Evening all, and welcome back to another video. Variable frequency oscillators, or VFOs. If you're going to build a transmitter, or a homebrew one certainly, you're going to need one of these, unless you want to be rock bound and use a crystal. So today we're going to have a look at valve VFOs in particular, because that's what we like here at the WTF. Lots of vintage technology, and we're going to see what the problems are with VFOs, particularly valves, as I mentioned, and to see if there's any way of getting them to behave, getting them to be a bit more stable. That's one of the big Achilles heels of using a VFO, and particularly with a valve VFO. Right, so as you can see, we've got in front of us a number of VFOs, variable frequency oscillators, and as you'll notice, three of them are actually identical, and I'll tell you a bit more about those in a minute. And we also have this one here, which came out of a commercial rig and is solid state. So I guess it begs the question, why don't you use something more modern if you're going to build a transmitter? I mean, there's various things out there which you can use, variable voltage oscillators, digital synthesizers and things like that. Well, we can do, but it's not really in the spirit of keeping things vintage with valves, because we love the valves, nice glowy things, and it's a lot. I think they're a lot more interesting to build up compared to solid state. But we have got a solid state one here. I'm quickly going to show it to you. It won't take too long with that, because obviously that's something else. But it's a good example of the alternative which you can use if you wanted to build a homebrew transmitter, or even a receiver where you've got to have a local oscillator which is stable. So this VFO here came out of a commercial rig. I'm not sure what it was, possibly an FT101, but if anybody recognises it, please feel free to leave a comment below, and it's always interesting to know where these things come from, but I have no idea. I think this came from a radio rally, but you can see that it's obviously well built, nice and sturdy, and it's got this reduction drive here, which is geared and everything. So it ticks all the boxes in terms of mechanical strength, stability, and general high standard of construction. And you can't really see the internal components on this. There's a PCB right down the bottom there, and that's got a few transistors and everything. So it's it's pretty standard solid state VFO. Now the problem with VFOs in general is, even if they're solid state, is drift. Now drifting can be a real problem. If you've got a solid state VFO, you might be looking at several tens of hertz every hour. That's actually pretty good. So 50 hertz an hour is actually quite acceptable. It's not brilliant, but in terms of having a QSO, you'd probably get away with that. Now some VFOs drift quite extensively, and this can be a real problem, especially if you're operating CW. It's nothing worse than some guy on the other end telling you that you're off frequency, and he's having to follow you up the band or down the band, as the case may be. So it can be a bit of a problem. Usually with CW, it's you're forever having to readjust if you're using a conventional valve VFO, and even with the solid state one, the last rig that we built, the GU50, even that had quite an exceptionally well made VFO, and even that drifted quite extensively, and it was a bit annoying. So what I've got to show you tonight is actually a VFO stabiliser, and I wanted to see if we could use that to try and tame a tube or valve VFO. And I'm going to show you these units that I've managed to find a few years ago, and see if we can use one of these to perhaps use in a transmitter, but see if we can stabilise it as best we can. So these are the three units that I've actually got. Now they've got these in a barn find, and these are XMOD surplus, and I have absolutely no idea what they came out from. I presume some old school XRAF, because I think most of the stuff that we got from this barn find was aviation related. So probably some sort of RAF transmitter, receiver, something from the 50s or 60s. And these are marked as an oscillator unit. That's about it really. And I can't really give you any further details in terms of where they came from. So again, if anybody knows or recognises them, I think it would be quite interesting to see where they actually originally came from. So we'll have a look at one of these in a little bit more detail, and then we can show you what the principles of making a half decent VFO are all about, because these units do demonstrate some of the sort of good practice in terms of making a stable variable frequency oscillator. So looking at one of these units in a bit more detail, you can see that they're quite well made. They're actually made of solid brass, and they've got a sort of a silver coating on them. I think it's what it is. It's a sort of silvered surface finish, which again will aid screening and also helps dissipate any heat. So they come with a screening can, and underneath there's not much to it really. Just hold it. There's a few decoupling capacitors there, and I've actually added that coupling capacitor to measure the frequency, so that's actually not an original part there. And then you've got an octal valve base, and the valve that goes in there is a, if I can find it, a 6J7G pentode. So that's the oscillator unit, but what I want to show you is actually the inside of it, and I've got one over there which I've already opened up. So what we will do is we will take a look at that. Right, so this is the inside of one of these units, and it's just a simple tune circuit. Ignore the LED for the moment, I'll tell you a little bit more about that in a minute. So you got variable capacitor, which is about 50 pf I would say. Then at the back there is the coil, and there is a slug in there which you can adjust. So it does demonstrate all the principles of building a VFO. It's got to be solid, ideally some sort of highly conductive material, copper, brass, aluminium's fine, but it's more commonly available. And it's got to be solid really, because any jolts and anything will cause the frequency to drift. The material that they've made it from is obviously to try and conduct the heat away, and also for screening. So it really does demonstrate, the principles of a good VFO. I've actually managed to trace out the circuit of this, and I will show you exactly what this, or should I say how this VFO is being wired up. So this is the circuit of this VFO, and It's essentially what they call an electron coupled oscillator. So we have the tune circuit here, and we've got a coil, as mentioned, with a tapping which goes to the cathode of the 6J7G. It's quite a standard circuit. I think the other name for this is a Hartley oscillator, or this type of oscillator is very similar to a Hartley oscillator. Most of these components, the 100K, all these components are the ones that we saw next to the valve base, and all these are inside the can. And that's it really. Now, the original specifications, when I connected one of these up with a valve, measured the actual frequency of oscillation, it's 4.902 to 4.761. So with a little bit of a tweak of the slug, and I think it'll probably cover sort of 5 megs to 4.8 thereabouts. So it looks to me like these VFOs are probably from, probably a local oscillator from perhaps a receiver. But in any case, these units will make quite good VFOs for any sort of project really. In fact, what I've done, the one that I showed you close up, I've actually rewound the coil, so that I've made so that actually it oscillates on 3.5 megs, so the CW end of 3.5 megs. So what we can do, we can use that actually for a transmitter, a VFO controlled transmitter, which I think I will probably build up. So the question is, we know these valve VFOs are notoriously drifty. Is there any way we can stabilise them? Well, I decided that I would sort of trawl the internet and see what's out there in terms of VFO stabilisers. And I think I found something that I think more or less works, or certainly reduces the drift down quite significantly. Well, after quite a bit of trawling the internet looking for a suitable VFO stabiliser, this is what I came up with, and I have to credit Hans Sommer's website, where he's got a lot of information on VFO stabilisers, particularly what they call Huff Puff VFO stabilisers, which this is a type of variant. The stabiliser, as mentioned, is what they call a Huff Puff stabiliser, and it consists of a 74HC164, which is an 8-bit shift register, and a 74HC6060, which is, I think, some form of counter of some description. So, without getting too involved in how this all works, the bottom line, and this is the way these Huff Puff stabilisers work, is that they're really comparing the input frequency with a clocked input or oscillator, and by some magic you get an output which changes the frequency of the VFO, or corrects the frequency of the VFO, and that is affected by using either a varactor, in other words, a diode where the capacitance across it varies, or using an LED, or you can use any old diode actually. So when you put it in reverse polarity and apply a potential across it, you get a corresponding change in capacitance, and that you can then use to correct the capacitance in the tuned circuit, and hopefully then correct the frequency. In this case, I've admitted all this because obviously I've got my own VFO. This actually forms part of it, a self-contained VFO in all this circuit, so I don't actually need all this, so I have omitted that. And I've put this all onto a little board which I'll show you, and I think it more or less works. It certainly slows down the drift of the VFO. I'm not sure if it corrects it 100%, but it's certainly a lot better than what it is, and I think we'll have to put it into practice to see whether, you know, all this would work in a usable transmitter. Anyway, let's show you the board that I've built, and we'll take it from there. This is the little board that I've built up of that circuit. So we've got our two integrated circuits there. That's the shift register, and that one over there is the binary counter, the 74HC4060. Couple of transistors that you can see as per the circuit diagram, and I've got a 5-volt voltage regulator, and that's my 60 megahertz crystal oscillator, or oscillator, and that's about it. Now I think what we should try and do is connect this up, or connect to one of these VFOs, give it a little bit of a warm-up period, and see what the drift is like. Right, I've set everything up here. We've got a knock-up power supply there, supplying about 150 volts. The VFO stabiliser is connected up to the VFO, and we've got a frequency counter which I haven't connected. So let's turn it on and see where we are. Right, we'll just turn on the HT. Looks like we've got something. At the moment we've got a frequency of 3.5 decimal 32. Now I've literally just turned this VFO on, so we really need to give it perhaps half an hour just to warm up and settle down before we can start sort of making any sort of reasonable comparisons. At the moment the VFO stabiliser is actually off, and you can see that it's for a valve VFO, this this unit is actually, it's not too bad. It's staying reasonably well put. But I think what we need to do is come back and then just try it with the stabiliser and without the stabiliser and see what happens. I've let this thing warm up now for about half an hour, and if you can remember what the frequency readout was when we started off, it's drifted down possibly about plus or minus 500 Hertz. So it hasn't drifted, considering that was a warm-up period, it's not excessive for a VFO of this type. So I'll put the frequency stabiliser on, and we'll give it 15 minutes and see how much it drifts. Which has obviously brought it back up to 3.5 megs. And we'll just wait and see. There's no jiggery pokery here, I'm just literally allow the half an hour warm up, and then we'll see how much it drifts down or stays the same. Okay, I have had this on now for 15 minutes. Started at 8:15 and it's now just after past. So looking at the frequency counter, it hasn't changed that much. It's sort of been hovering around about decimal 10, and it goes to sort of 0.07, which isn't too bad. So I would say it's pretty well smack bang on frequency compared to where we left it. So what I'll do is I'm going to turn the stabiliser off. The frequency will obviously drop a bit so once the stabiliser is turned off, but then we'll take a new reading on the frequency counter, and then we'll give it another 15 minutes and see what happens. So the frequency stabiliser is now off, and we'll give it another 15 minutes and see what the drift is like. Right, so another 15 minutes and have a look at the readout on the frequency counter. So it has dropped in frequency slightly, but not a massive amount. It's probably drifted, probably only about 10, possibly 20 hertz. It just depends on the accuracy of my frequency counter. But I think you'll agree that I think the stabiliser does work. I may have overestimated my VFO and insulted it somewhat by saying that it was drifty, because it's actually not that bad. It's actually quite a stable VFO, considering it's a valve VFO. But I think this circuit will, I think it will help, and I think it definitely makes a difference. I think if we were to conduct the test for longer, I think we might perhaps get even more meaningful results. But anyway, obviously we're limited with time and everything, but I think it does prove the point. Anyway, I think this is a circuit that might be worthwhile considering if you've got a drifty VFO. It's quite easy to do, and I think I would say that it does help. So next time we're going to put all this into a transmitter, and then that will be the real proof for the pudding, to see whether how stable it is in the transmitter. Anyway, thanks for watching, and see you again soon.